We've proved that every subspace is a span of finitely many linearly independent vectors, but it's sometimes useful to actually express a vector space as a span of some vectors. So let's look at an example. Here's a vector space. So you can take my word for it that this actually is a vector space. But let's express this vector space, let's call this capital V, let's express this as a span of linearly independent vectors. Now, how you do this really depends on how your vector space is written down. For this particular description of this vector space, one thing we can do is, if you look at the formula at the form of the vector that is defining this vector space, we can actually write this as the sum of two different vectors. This is 4a, 2a, and 0, so a vector with the a's, plus a vector with the b's, minus 3b, b, 2b, and a and b are scalars. But we can actually go a little bit further. Now in each of these individual vectors, so this is the same set of vectors as before. Now we can go a little further because in this first vector, every entry has an a in it. So this is actually 4, 2, 0 times the scalar a. And the second vector is the scalar b times minus 3, 1, 2. And again, a and b are scalars. But this collection of vectors here, I mean, this just by definition, this is the span of the collection 4, 2, 0 and minus 3, 1, 2. So we found vectors that span our original vector space V. I guess the only question now is, are these vectors linearly independent? So how would we check that? Remember, a nice way to check if vectors are linearly independent is sort of mash them into a matrix like this, and then check if this equation has any non-trivial solutions, which amounts to row reducing this matrix. So if we row reduce this matrix, let's see, we could switch the first and second rows, so we get 2, minus 3, 2, 1, 4, minus 3, 0, 2. And to have no non-trivial solutions, we just need to check that there's a pivot in every column when we row reduce. So let's see, we can subtract twice the first row from the second row, so 2, minus 1. We're going to get 0, and then minus 5, and 2. Okay, and you can see that we don't actually need to finish row reducing. We just need to know, is there a pivot in every column? Well, there's definitely a pivot in this column. And you can see we can use this 2 to kill off that minus 5, and then there will be a pivot in the second column. So there is a pivot in every column, so that means there's no non-trivial solutions. And that means that these two vectors, 4, 2, 0, and minus 3, 1, 2, are linearly independent. All right. Well, you can kind of see that the best case of, every vector space is the span of some vectors, but the best case is when is if we can express a vector space in terms of linearly independent vectors. I mean, if these vectors are linearly independent, then one thing that we've proved about a span of linearly independent vectors is every vector in a span of linearly independent vectors can be written as a linear combination in only one way, right? And that's sort of the nicest. It's sort of inconvenient to be able to write something in a vector space as more than one linear combination. So it's nicest to have a linearly independent set that spans. Another way to look at it is we can ask, if we have a linearly independent collection in our spanning set here, could we add or remove any vectors and still span V? Well, suppose we removed a vector. Just for sake of argument, say it's v sub k. So on the one hand, after we remove v sub k, what we're left with is the span from v sub 1 up to v sub k minus 1. What we started with was the span of v sub 1 up through v sub k. And I guess what we're really asking is it possible that removing a vector doesn't change the span? So is it possible that these are equal? Well, v sub k is definitely in this span on the right. So I guess the question is it possible that v sub k is in the span on the left? Well, if so, if this were the case, that means v sub k would be a linear combination of v sub 1 through v sub k minus 1. But this would mean that the original collection was linearly dependent, right? This is a linear dependence relationship. And we assumed at the very beginning that all of our v's were linearly independent. So v sub k can't be in the span of v sub 1 through v sub k minus 1 because of linear independence. So no, this can't happen. And that means that these aren't equal because there's a vector in the one on the right that isn't in the span on the left. So if you have a span of linearly independent vectors, removing one of those vectors changes the span. Okay, well, let's think about adding a new vector. And when I say a new vector, we should add a vector that isn't already in this span. Right? There's no point in adding a vector that's already in this span because clearly that isn't going to change the span. Well, if we add a vector v that's not originally in the span, well, in this case, right, so we're asking, is it possible that if we add this new vector v to our spanning set, is it possible that we get the same span as before? Well, no, because v isn't in this one, but v is in that one, clearly, because it's right there. So no, these definitely can't be the same. So spanning with a linearly independent set is the best because that means that every vector that shows up in your spanning set is a necessary part of producing the vector space, or the subspace that you actually started with, right? If you add or remove any vectors and keep this set linearly independent, then you get a different span, right? So spanning with linearly independent vectors is really the best.